Welcome to the Crazy Hat Chemist. So another video here on electrochemistry. So let's get moving. Bam! So today we are talking about what? Rules of assigning oxidation numbers and some examples following. Okay, so here are the rules for assigning oxidation numbers. Number one, all elements in their free state, uncombined with other elements, have an oxidation number of 0. So for example, we've got sodium metal, we've got copper metal, magnesium metal, we've got hydrogen, chlorine, and oxygen, and nitrogen, which are all diatomic. All of those elements in their standard state are going to be an oxidation number of 0. Okay. Number two, group number 1 is +1. Group number 2 is +2. And then the special 3 that are diagonal, well, I've got some of those right here. It starts with silver, which is a +1, zinc, which is a +2, and then aluminum, which is off the charts here, is a +3. Cadmium, of course, is right underneath zinc, and therefore it is also a +2, just like zinc. It's like it's in the same group. Okay? Number 3 is hydrogen is a +1. And the exception to this is when you have a metal hydride. And that is when hydrogen is combined with either group 1 or group 2, because group 1 is no matter what a +1, group 2 is a +2 when in a combination of a cation-anion form. And when hydrogen is combined with either group 1 or group 2, then the group 1 and group 2 takes precedence, and then the hydrogen is a hydride, which is a -1. All other cases, hydrogen is going to be a +1. Okay, rule number 4. Okay, number 4 is oxygen is a -2 oxidation number, except when with peroxides, where it is a -1, or when it's with fluorine, where it's a +2. Very simply, fluorine takes precedence. That deals with rule number 5. Fluorine is always -1. Okay? In addition to that, other halogens, the halide ions, right underneath fluorine, which is off my chart here, which is, so fluorine is -1, then chlorine, bromine, iodine, those would be the other halide ions or the halogens. Those are -1. Okay? Nonmetals with and lower halogens, that is. Number 6. The metallic element in an ionic compound has a positive oxidation number. And that goes back to saying that any one of these metals right over here, they're going to be cations. They're positive. They have lost electrons, and therefore the nonmetals, they are gaining electrons. We've already talked about that in nomenclature many, many years ago, it seems like. Okay, number 7, in covalent compounds, the negative oxidation number is assigned to the most electronegative atom. Okay, so in covalent compounds, so let's say carbon dioxide is a covalent compound. That's using binary nomenclature. Okay, that the negative oxidation number is assigned to the most electronegative element. So if I have carbon and oxygen in carbon dioxide, the more electronegative element, which is oxygen, would be assigned the negative oxidation number. That would be oxygen. Carbon would be assigned the electropositive or the positive oxidation number. Okay? Number 8. The algebraic sum of the oxidation numbers of the elements in a compound is 0. Okay? That's a very important component. Okay? The algebraic sum for number 9 of the oxidation numbers of the elements in a polyatomic ion is equal to the charge of that polyatomic ion. Okay? These are the rules for assigning oxidation numbers. You need to either memorize these rules or just write out a lot of oxidation numbers and examples, and then the rules, you'll just flat out memorize them. You should have actually already known your periodic trend charges, and that's what these are. Okay, group 1 +1, group 2 +2. Okay, and then the halogens are -1, and then we have that the halogens are -1, oxygen -2. Then we have that diagonal pattern of silver, zinc, and aluminum. +1, +2, +3. These are oxidation numbers that you should have memorized already before with nomenclature. So they tie into that. So let's do some examples using these assignment of oxidation numbers so we can get oxidation numbers for other elements that we don't actually fit within these categories. Okay, so we're going to write out all the oxidation numbers for all the elements in the following. So this first one here is copper. It's an element which is metal copper in its standard state, i.e. it's a solid at room temperature and pressure, and since it's an element in its standard state, it would have an oxidation number of 0. Really simple. Okay, then we have iodine. Now iodine is one of the 7 diatomics elements that we have. Okay, and iodine in its standard state would actually be a solid. Okay, so if iodine is diatomic in its solid state, then you would expect that it's an element in its standard state and it would have an oxidation number of 0. It's not combined with another element. Hopefully those make sense for you. Okay, then we have this polyatomic ion of nitrite. This is the nitrite ion. This is NO2 minus 1. So the first thing that we need to do is go back to that previous slide and look at the rules for oxidation numbers. So there are certain elements which have certain oxidation numbers, and then we can obtain the other ones from that. And one of those elements is in this polyatomic ion, and that is oxygen. So oxygen followed a particular set of rules for its oxidation number. It is going to be a -2 for the most part, -1 in peroxides, and a +2 when with fluorine. Well, this is not a peroxide, and it's not with fluorine, so therefore the oxygen is going to be a -2. So that's one that we actually know. Okay, that's based on the rules of which we have defined previously. Now what we need to do is we need to solve for the oxidation number for the nitrogen. So if you look on your periodic table, you would predict that the oxidation number for nitrogen is going to be a -3. And this is based on just its location on the periodic table and going back to that nomenclature unit. Okay, all right, so let's see if we can actually solve for the oxidation number of nitrogen. So it's nitrogen, there's our little mathematical algebraic equation that we're using. Nitrogen plus 2 oxygens, which is equal to -2 each. So that's that 2 outside the parentheses lets us know we have 2 oxygens. Inside the parentheses is the charge on the oxygen itself. And the charge on this polyatomic ion is equal to -1. Therefore, the sum of these is all equal to the charge on that polyatomic ion. So now what we're going to do is we're going to say nitrogen -4 is equal to -1. We're going to solve for this nitrogen. We're going to add 4 to both sides, and then we get a nitrogen as a +3. So the oxidation state for this nitrogen is a +3. Okay, now that should come back to that question that or statement that I had made already before, and that the oxidation number or the predicted charge on nitrogen was a -3. Okay, and that was just based on that nomenclature unit way back a long time ago. However, okay, oxygen takes precedence, and therefore its oxidation number is negative. Okay, and then the nitrogen is therefore going to be positive as a result. Okay, and so this is why we have to solve for the oxidation number for other elements beyond the ones that we've defined on the previous slide. Okay, so these are arbitrary numbers. So now we know that nitrogen is a +3 in the nitrite ion. Okay, now we're going to look at the nitrate ion. The nitrate ion has a nitrogen in it. It also has an oxygen, this time 3 oxygens, and its overall charge is a -1. So now what we're going to do is we're going to look at this and say, do I have an element with the standard oxidation number charge that I've defined by my set of rules? And that is yes, and that is oxygen is a -2. Now what we need to do is we need to solve for the oxidation number for the nitrogen in nitrate. Okay, and here is the mathematical equation associated with this. I am solving for nitrogen. There are 3 oxygens. Each oxygen is a -2, so there are 3, and then the oxidation number for oxygen is -2, and the charge on the polyatomic ion is -1. So I'm going to solve for the nitrogen here. That's solving for X, if you will, and I get nitrogen is equal to a +5. So you should see that nitrogen can be at least 2 different oxidation states here from what we have defined or what we have solved for thus far, which is a +3 and a +5. If nitrogen is diatomic, it's a 0. And there are other oxidation numbers for nitrogen. Actually, nitrogen has one of the elements with a large number of oxidation states, and you do have to solve for it. Okay, let's do another one as another example. Okay, and this is S2O32-. This is also a polyatomic ion. So what element do we know the oxidation number from our set of defined rules? And that is oxygen is a -2. So therefore we do not know the sulfur. Now in this case there are 2 sulfurs in this compound, or sorry, this polyatomic ion. So it's 2 times the S plus 3 oxygens times the charge on the oxygen, which is -2, is equal to the charge on that polyatomic ion, which is -2. Now what we're going to do is we are going to solve for S. So if you don't like the variable S, then you can replace it with an X, and you should be able to solve this for X then. And you're going to get sulfur as a +2. Again, that doesn't really follow what we learned on our periodic trend charges, but these are oxidation numbers, okay? So the charge on the oxygen is defined at -2, and then we solve for the other element or elements, and that would be the sulfur, in this case at +2. Let's do another one here. We've got calcium phosphate. So calcium is a group 2. And because it's a group 2, it has a standard oxidation number that is known, defined, and that's a +2. And also we have oxygen, and this is not a peroxide, and it's not with fluorine, so therefore the oxidation number for oxygen is a -2. So we have 2 of them, of the elements in this compound of calcium phosphate that we know. One of them is the calcium at 2+, one of them is the oxygen at 2-. And now what we need to do is we need to solve for the phosphorus. So there are 3 calciums at 2+ each, plus 2 times the phosphorus, notice that 2 outside the parentheses, plus 8, that's 2 times 4, there's 8 oxygens at 2-. Now this is a compound with a net charge of 0, therefore it equals 0. So now what we need to do is we need to solve for P, or X, whatever you want to call it, and we're going to get the following. Phosphorus is equal to +5. So the oxidation number in calcium phosphate for phosphorus is +5. In fact, what I want you to do is I want you to write out the polyatomic ion phosphate, which is PO4 3-, and solve for the oxidation number of phosphorus in just phosphate. You should also get phosphorus as a +5. Bam. Okay? That is another Crazy Hat video by the Crazy Hat Chemist, and of course I am the Crazy Hat Chemist, and that's why I have got a crabby hat. So I'm not going to be crabby as long as you give me a thumbs up on this video. I'm not going to be crabby when you subscribe to my YouTube channel. I'm not going to be crabby when you Google me and you find the Crazy Hat Chemist and you find my website, which my son designed, and get yourself a sticker or maybe even a t-shirt. Okay, I hope you have a fantastic day, and please give me a thumbs up, subscribe to my YouTube channel, pass it on to all your cool chemistry friends, and everyone that's in your class. I will see you next time. Bye for now.